Welcome to the fourth episode of the DigiBUILD project podcast, where we explore the most important achievements of the project from a technological perspective. My name is Matteo Filippini and I'm a project officer at Euroheat and Power. And today we are going to discuss about digital twins and cloud-based DigiBUILD data toolbox. And my host is Leandro Lombardo from ENG. So, Leandro, let's start with the first question. Could you introduce the digital twin concept in DigiBuild project?
Yes, of course. In the DigiBuild project, several digital twin services have been developed to address the specific needs of the stakeholder involved. However, before introducing the concept of digital twins within DigiBuild, I think that it's important to briefly define what a digital twin is in general terms. Various definitions of digital twin exist in the literature, but there is a commonly accepted understanding. We can say that a digital twin is a virtual replica or digital model of a physical object, process, or system that enable real-time monitoring, analysis, and optimization. While many definitions focus on physical systems, such as machine, building, or industrial infrastructure, it's important to note that the digital twin can also represent digital processes or conceptual systems. To be more precise, we can also refer to the ISO standard definition that defines a digital twin as a digital representation of a target entity with data connection that enable convergence between the physical and digital states at an appropriate rate of synchronization. It is clear to understand that this definition highlights a key concept of a digital twin. It continuously updates itself to reflect the real-time state of the target entity, ensuring that the digital model remains closely aligned with the physical counterpart. These core concepts have been adopted in the DigiBuild project to design and implement our digital twin that support real-time data integration, simulation, and informed decision-making in the built environment.
Okay, interesting. Second question. So, based on this definition, it is normal to ask what is not a digital twin.
Thanks for the question. The concept of a digital twin is often misunderstood. Sometimes tools or technologies are also mistakenly associated with the terms, even though they do not meet the fundamental requirement of a digital twin. In DigiBuild, to avoid falling into error, we did a preliminary analysis to figure out which should not be considered a proper digital twin. Let me try to do some example of what does not fall within the definition of a digital twin. For example, a simulation without integration with the real data. If we have a simulation or predictive models that use historical or synthetic data to simulate the behavior of, for example, a system, it is not a digital twin. A simulation model that is not updated continuously with the real data or not connected to physical sensor and device cannot be considered a digital twin. Another example can be a non-interactive monitoring system. If we talk about a passive monitor system that collects data without integrating and using this information to make a decision or take action, it does not represent a digital twin. Or sometimes the static data archives or database is defined as digital twin. It is not true. While historical data can be used by digital twin for predictive analysis or performance improvement, the lack of continuous synchronization between the real world and the digital model renders such archives only a data resource, not a digital twin. Also, another example is machine learning models without real-world integration. Machine learning models or artificial intelligence algorithms that are trained on dataset but not integrated with the target entity or continuously updated with the real-time data cannot be considered a digital twin. A digital twin uses the continuous convergence of real-world and digital data to optimize and make decisions in real time, whereas an AI models without the direct interaction does not fit this definition. Another example to finish is, for example, the augmented reality or a virtual reality solution without the real-world integration. Augmented reality or virtual reality technologies can be used to display digital models immersively, but without a continuous flow of real data updating these models in real time, these technologies do not constitute a digital twin. Therefore, we can say that a digital twin is not a simple representation, digital representation or model of a target entity. For it to be defined as such, there must be a continuous synchronized connection between the real world and the digital model, with the goal of monitoring, simulating, optimizing, and making a real-time decision.
So, at this point, my third question would be, could you please briefly tell us what kind of digital twins were implemented in DigiBuild project?
Thanks for the question. In the DigiBuild project, different digital twin services were developed to meet the requirement of the project stakeholders, as we said previously. The areas of the digital twin services are related to the building and the smart energy network, covering the following main dimensions: better informed planning of building infrastructure, designing future building and the building process, and energy efficiency building and district scale management and operation. The digital twin of the DigiBuild project are, as we said, the virtual representation of real world entities. In our case, primarily building. They use synchronized real time and also historical data to reflect both the past and the present behavior of the target entity that they replicate. In addition, we can also highlight that our digital twins benefit from artificial intelligence services developed within the project that are based on machine learning models and also optimization technique to support decision making, mainly for building manager, that is our main stakeholder. Some of the DigiBuild digital twins are also capable of acting as a control instance, meaning that they can send command directly to the physical entity if ready to receive it. It is a very important aspect of maturity of this digital twin. The DigiBuild digital twins, let me say that they cover different areas like the digital twin for designing future building, digital twin for optimal energy management, digital twin for planning of building infrastructure, or district digital twin and district network digital twin. And all of these digital twins also exploiting capabilities of project services are very helpful, providing final user with, for example, energy usage prediction based on machine learning algorithm that can allow facility manager to foresee energy peaks, avoid, for example, unnecessary cost, and plan ahead for demand response. or fault detection diagnostic to constantly monitors the building system, detecting anomalies, for example, or inefficiencies, ensuring proactive servicing before this situation was seen. Or, for example, comfort prediction and optimization to predict thermal comfort level from real-time data captured by temperature, humidity, and occupancy sensing sensors in order to maintain optimal comfort while also conserving energy. Let me say that we can say also that the DigiBuild digital twins, as I anticipated previously, reached a different maturity level that span from 3 and 4 based on the EAT spectrum, that is the scale adopted as a reference within the project.
Okay, I see. Thank you for the exhaustive reply. I have another question. Could you better explain this concept of maturity level in DigiBuild? You introduced the IET spectrum, is it correct?
Yes, that's correct. We adopted the EAT maturity spectrum in DigiBuild. We can say that when analyzing different digital twins, it's important to recognize that they are not all the same. They differ, for example, in feature, capabilities, and the way they interact with the physical world, the real world. To capture this difference, several classification models have been proposed, often focusing on the development stage and maturity level of a digital twin. In the DigiBuild project, we chosen to follow the approach developed by the Institution of Engineering and Technology, the EAT, the acronym. Their framework introduces a maturity spectrum ranging from a level 0 to a level 6, which helps assess how advanced a digital twin is in terms of integration, functionalities, and interaction with the real-world system. The spectrum spans from a basic digital replica of a physical entity, we consider it the level 0, to a fully autonomous digital twin, the level 6, capable of independently acting on the physical system and adapting to changes without the human intervention. This is the best level for a digital twin. This model has guided the design and the development of our digital twin services within the project. And as I already said previously in the previous question, our digital twin reached the level 3 and 4 of this spectrum. In particular, the level 3, also named as active connection, it features a real-time connection with sensors, IoT device, and other dynamic data source, actively reflecting the state of the physical system. While the level 4, also named as integrated models, let me say that digital models not only in this level receive real-time data, but also integrate predictive or behavioral models to simulate future action or changes.
Well, thanks for the clarification. Okay, now let's go back to the digital twins developed during the DigiBuild project. Could you tell us how the end user can access them?
Thanks for asking me. The digital twin developed within the DigiBuild project can be accessed easily online through a dedicated cloud toolbox. This platform offers a user-friendly and centralized interface to explore the project digital twins and related services.
All clear, okay. And last question. So before we leave, I would like to ask you, what is the advantage of this cloud-based toolbox?
Yes, great question. The main advantage of the cloud-based DigiBuild toolbox is that it offers users a single centralized access point to all digital twins and services developed within the project. And it also provides a clear overview of their key feature, real-world application across the pilot cases. We know also that digital twins typically require large volume of data and significant computational power for analyzing and simulation. By using a cloud-based infrastructure, DigiBuild ensures the scalability and performance needed to process both real-time and historical data efficiently and run machine learning models. This setup supports advanced technologies like IoT, artificial intelligence, and machine learning also. Additionally, to conclude the answer, the cloud enable centralized management, easier data access, and smoother collaboration among teams across different locations. That is also the case of the DigiBuild project.
Thank you for listening. I hope you found the discussion insightful, and we look forward to sharing more about our work in future. Goodbye.